Okay, probably the last section we'll do in chapter 4 is 426, details of a multi-pole generator. It's not that the other two sections aren't important. It's, I guess, one of those things where there's other things that are probably more important. So we'll wrap this chapter up with completion of this chapter. And what we'll do, we'll look at some particulars of a more realistic generator, kind of figure out which way to turn my head here. And then also let's look at this figure 437 too. I think that's kind of interesting to look at. Figure 437 shows a DC generator, a DC Thompson generator installed in 1889, and it was used to light the streets of Montreal. It delivered a current of 250 amps. Can you imagine? 250 amps, that's a lot of current, at 110 volts. And then it's also showing some of the characteristics of this machine. Look at that thing. The speed is 1,390 RPMs. Look at the weight, almost, gosh, what is that? Close to 5,000 pounds. The armature diameter and the stator internal diameter. Look, here's the commutator bar and the conductor size. You know, and it's a modern generator having the same power and speed weighs 7 times less and would occupy a third of the space of that big thing. One thing I'll say kind of quickly here, you know, if in the future, if you find yourself going to places that maybe you went as a kid, I know the last time I took my son when he was a lot younger, we went to the Smithsonian, and in the science and technology building, they have a lot of these old electrical machines and stuff there. And it's really cool to see those. You know, these designs were done before computers, and the fact that they actually work is pretty amazing in some ways. But the last thing I really want to talk with you about was, you know, just kind of want to talk you through this schematic of a 12-pole 72 coil um, uh, DC generator. And you know, just to kind of walk through some things, you know, how do we know it's 12 poles? Well, we can count them, right? And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 poles. It says it's 72 coils. So if we were so inclined, we could count each one of these represented coils across here, and we'd find that ultimately there were 72 of them. What else would we find? That we would find the brush sets and how they're connected. All of them ultimately, the positives and the negatives would be interconnected, so that you know, when we went to pull the voltage off of the machine, we would see the effects of the total number of coils and so forth and so on. But let's, I think it's kind of neat what he does here. This, you know, 72 coils. If there's 72 coils, there has to be 72 slots for those coils to reside in. If there's 72 coils, there has to be 72 commutator segments. You know, so all that works together. You know, we talked about that earlier in the chapter. But what's kind of neat is here's figure 438, you know, and this is the total 12 pole, 72 coil generator. And then what he does is he takes a segment of that and he just blows it up. And what I think is cool about this, you know, we talked about these neutral zones. And, you know, when we think outside of, you know, more than a two-pole generator, here we see this coil, right? So here's a coil. Just let me get the drawing mode here. So here's a coil right here, right? And then, you know, here's, you know, another one running this way. But what we wanted to see is that when this particular coil is being shorted out, we want to make sure that it is in the neutral zone. And so, you know, we're seeing that occur when we blow up this um, drawing of this, right? So here's A, going to here, and we see it, as it's 72 and 1 are being shorted out, that conductor, which runs, the length of that armature, it is residing in a neutral zone at that particular point. And, that was the whole idea with the design, is that we wanted to assure that that occurred. But look at the complexity of this when you bring in 72 coils and 72 commutator segments. It really gets complicated, doesn't it? And so, but for each one of those, when those that coil is being shorted out, the length of it, again, it runs, the length of that coil runs the length of the armature, and when it's being shorted out, it is residing in the neutral zone, and that way we don't get the arcing and sparking through there. A little problem, and we'll look at this in just a second. He says the generator in figure 438, this is example 4.2, generates 240 volts between adjacent brushes and delivers a current of 2400 amps to the load. Calculate the current delivered per brush set, the current flowing in each coil, and the average voltage induced per coil. So what he's saying here, and we'd go through the rating here before we got to doing this problem, but he says there's a current of 24 amps that flows out of the positive terminal and back into the negative terminal of the generator. There are 12 brush sets. We can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's 6 that are positive and 6 that are negative. Okay, so the current per brush set, the current per brush set would be 2400 divided by 6, or 400 amps. And that's not a hard thing, it's just understanding the construction scheme. And then the other thing, he says the current flowing in each coil. Well, so part A, let's see, part A is saying what is the current per brush set, the current flowing in each coil. So each positive brush set delivers the current from the coils to the right and to the left of the brush. Consequently, the current in each coil would be 400 divided by 2, because of the construction of this thing. So it would be 200 amps per coil. There are 6 coils between adjacent brush sets. So the average voltage per coil would be 240 volts divided by 6, or 40 volts. Okay, so if we could go between each one of these, we'd see 40 and 40 and 40, and we do that 6 times. 1, 3, 4, 5, 6, and we would say that there are 6 40s, or 240 volts between brush sets. Okay, so let's wrap this up for chapter 4. 427 is talking about ideal commutation process. And then 428 tells us what really happens, a practical commutation process. And since we're not going to do much interaction with DC generators probably ever, we'll let that go at this point and say that we're wrapping up chapter 4. So I hope that you've gone through these videos. I've taken a lot of time to make them for you. They are equivalent to what we would be doing in class. And again, as you're going through this, I hope they're not just wearing you out. What I would hope that you would do is just bite off 2 or 3 of these at a time and go through them and try to make sure that you understand what's happening and proceed through this. And then I'm matching up some homework problems to go through it. And we've done a lot of detailed discussion here, and it's going to pay off for us down the road. in this understanding and talking about the internals of these electrical machines. And we'll see that everything that we talked about in chapter 4 is going to apply to everything else in the rest of this course.